Hey everyone, welcome back to the channel. In today's video, I will be talking about the most popular and widely used optimizer in deep learning, Adam. And if you have training neural networks, and then you have probably heard of it. But what is it and why it's so effective? Let's break it down step by step. First thing first, the ADAM stand for the adaptive moment estimation. And it's an adaptive learning rate optimization algorithm that computes individual learning rate for each parameter based on both the first order momentum and second order acceleration of the gradient. In simpler terms, ADAM combines the benefit of two most other popular optimization, momentum and RMS props. It adapts the learning rate of each parameter during training, which help us to converge faster and reduce the need for manual learning rate tuning. So why is ADAM so popular? So here are key advantages. The first one, adaptive learning rates. It automatically adjusts the learning rate for each parameter, which is really helpful when training large complex model. Second, computational efficiency. So ADAM uses only the first order and second order moment estimates, so making it more memory efficient than some other optimizer like LPFGS. Third, the bias correction. So it includes built-in bias correction for small gradients, which helps to stabilize early training stages. And the fourth, grade default. It's just generally a good default optimizer for most tasks, whether you're training CNN or RNN or transformers. But it's not all perfect, and there are some downside to keep in mind. Right. So also let's talk about the few pros and cons of the atoms. The first one, again, the adaptation of learning rates. As mentioned, ADAM adapt the learning rate based on the data and the training progress. It reduces the need for manual tuning. Next is convergence speed. So in many cases, ADAM converge faster than traditional optimizer like SGD, stochastic gradient descent. Works well with spare gradient. It's great for problems where gradients are sparse, like in the natural language processing or computer vision. Some of the cons of atoms would be the overfitting. Sometimes atom can lead to overfitting, especially in the smaller data set because it might converge to sharp minima. The hyperparameter tuning. While atom default parameter works well most of the time, you still may need to tune hyperparameters like learning rate and others for optimal performance. Less theoretical foundation. So there is less theoretical understanding of atoms compared to optimizer like SGD. So it may not be the best choice for every use case. Now let's dive a little deeper into the atoms works, how atoms works behind the scene. And atoms uses two key important components. First, the momentum, and second one is the adaptive learning rate, and that's the scaling of learning rate. So momentum, it is an exponentially decaying average of past gradients, which helps smooth out updates and give the optimizers a bit of memory. So this prevents it from getting stuck in the sharp or poor quality minimum. The scaling of learning rates. So Adams also adopt the learning rate by using the second moment estimate. So this is essentially an exponentially decaying average of a past square gradients, which helps to adjust the step size. Now let's take example of some code to see how Adam implemented in practice. So for this, let me first import the libraries. Right. First, we are also preparing load the MNIST dataset. Once the library get installed, right? And let's normalize the images. So images are normalized to range 0 and 1. The image are flattened from 28 by 28 to 784 dimensional, a single vector per image. And let's check the shape of the training labels. Right. It was 60,000 images. And let's convert to the one hot encoding to the categorical type. And let's check the labels after conversion. Cool. Now let's create the model. So we are using the TensorFlow sequential API, and there are two layers, input layer and output layers. So input layers has 128 neurons with ReLU activation, and the output layer has 10 neurons, one for each digit in the MNIST. Let's compile and let's fit the model. So in this, the optimizer uses Atom. So Tensor uses the default setting of the Atom optimizer. And the loss function is categorical close entropy, suitable for multi-class classification. And the metric stack is accuracy. So after we train the model, we'll evaluate the results. And we'll print out the test accuracy and the test loss for after evaluation, which looks really good compared to we got 97% of accuracy. And at the end, we can also hypertune the hyperparameters of atoms in TensorFlow. Like this, in this example, you can manually specify the hyperparameters and then compile the model. So we can manually set the training rate like 0.001, which is typically default, the beta 1 0.9, and also epsilon is a small constant added to the prevent division by 0. So we can set it to some value. So the Atom optimizer in TensorFlow is easy to implement and typically provide great performance using minimal tuning. It combines the advantage of momentum and adaptive learning rates, making it an excellent default choice for many machine learning tasks. However, keep in mind that tuning the learning rate and other parameters can still be important, especially for the complex models. Yep. Thank you for watching. I'll see you in the next one.